Multi-round human AI collaboration with you specified requirements. Simon Orania *1, Jan Kiania *1, Kane Tasani1, and George Pappas 1. University of Pennsylvania. Oanis, Jank, Asani, Katastatsis, and Abstract. As humans increasingly rely on multi-round conversational AI for high-stakes decisions, principled frameworks are needed to ensure such interactions reliably improve decision quality. We adopt a human-centric view governed by two principles: counterfactual harm, ensuring the AI does not undermine human strengths, and complementarity, ensuring it adds value where the human is prone to error. We formalize these concepts via user-defined rules, allowing users to specify exactly what harm and complementarity mean for their specific test. We then introduce an online, distribution-free algorithm with finite temporal guarantees that enforces the user-specified constraints over the collaboration dynamics. We evaluate our framework across two interactive settings: LLM simulated collaboration on a medical diagnostic test and a human crowdsourcing study on a pictorial reasoning test. We show that our online procedure maintains prescribed counterfactual harm and complementarity violation rates even under non-stationary interaction dynamics. Moreover, tightening or loosening these constraints produces predictable shifts in downstream human accuracy, affirming that the two principles serve as practical levers for steering multi-round collaboration toward better decision quality without the need to model or constrain human behavior. One introduction: conversational engagement with AI systems is already happening at massive scale, with humans increasingly relying on multi-round interactions to guide real-world decisions in domains ranging from medical triage and legal research to personal finance and everyday planning. In these settings, the AI participates in an evolving dialogue, refining information over multiple rounds as the human asks follow-up questions, challenges earlier outputs, or requests clarification. Despite the prevalence of this mode of interaction, we still lack principled ways to evaluate whether such collaborations are working well or to design them so that they reliably improve decision quality under uncertainty. Historically, both classical 8 and recent work 20 has often conceptualized collaboration through the lens of agreement. Multiple agents interact in order to reconcile beliefs, converge to a shared posterior, or reach consensus. While this perspective has yielded deep theoretical insights, it implicitly treats the human and the AI as symmetric agents with comparable authority, responsibility, and incentives. In practice, however, this symmetry assumption is fundamentally misaligned with how computational correspondence Honorani at cs.append.edu and jank at cs.append.edu. 1 args 2602.17646C1 status.ld 19 2026. AI systems are deployed and used. Humans, not AI systems, are ultimately accountable for decisions and their consequences. Moreover, engagement with an AI system is itself a human choice. The human decides whether to consult the AI, how long to continue the interaction, how much trust to place in its responses, and when to disengage altogether. Motivated by this asymmetry, we adopt a human-centric view of collaboration. We ask how a human-AI interaction should be designed to incentivize a human to engage in it in the first place. From this perspective, a successful human-AI collaboration must satisfy two minimal requirements. First, interaction with the AI should not undermine the human's existing strengths. Properly, we refer to as counterfactual harm. If the human is already poised to make a correct judgment, engaging with the AI should not degrade that outcome. Second, the collaboration should create genuine value, precisely in situations where the human is likely to err, by helping recover correct outcomes that the human would otherwise miss. Properly, we refer to as complementarity. In this work, we introduce a carefully designed algorithmic framework for multi-round human AI collaboration under uncertainty. Our framework allows for an arbitrary flow of information between the human and the AI through natural language interaction, while governing the collaboration dynamics in a principled manner so as to satisfy the two requirements of counterfactual harm and complementarity. Along the way, our contributions stand three fronts: at problem formulation and modeling. In section 3, we propose two key modeling contributions. First, we introduce an interaction protocol in which a human and an AI collaborate on solving one problem at a time through a multi-round dialogue. This model captures the sequential nature of conversational interaction while providing an explicit algorithmic handle over the AI's uncertainty quantification, which can be shaped to enforce different collaboration constraints. Second, we develop a general framework for specifying constraints on collaboration dynamics through user-defined indicator functions of counterfactual harm and complementarity. These indicator functions allow a wide range of meaningful application-specific notions of safe and productive collaboration to be translated into concrete constraints on how the AI communicates uncertainty. Roman 2 algorithms and guarantees. In section 4, we develop a finite sample online collaboration algorithm that can provably enforce user-defined collaboration constraints over time. Our guarantees hold without any assumptions on the distribution of problems, the human's behavior, or the internal mechanisms of the AI system. Despite this generality, the algorithm ensures that the AI's uncertainty communication adapts online so as to satisfy counterfactual harm and complementarity constraints throughout the interaction. Roman 3 extensive experiments. In section 6, we provide an extensive empirical evaluation across two complementary interactive settings: LLM simulated collaboration at scale and a real human crowdsourcing study. 1, we empirically validate that the online procedure maintains the prescribed counterfactual harm and complementarity violation rates over time even under non-stationary interaction dynamics, and B, show that tightening or loosening these targets produces predictable shifts in downstream human decision quality, confirming that the two principles act as practical levers for steering multi-round collaboration. One code available at github.com/noranisma/multiround collaboration/2. Two related works. In this section, we only focus on closely related literature and provide an extended discussion in Appendix B, Human AI Collaboration Through Prediction Sets. A growing line of works that is prediction sets of interfaces for human decision support 933, 63, 64, 68. These works generally treat the AI's output as a static hint and consider only single-round interactions, leaving open the question of how to handle iterative refinement where a human may update beliefs or revise proposals across multiple rounds. Our framework builds upon 48, which provides the conceptual foundation for formalizing collaboration through prediction sets via counterfactual harm and complementarity. We extend the single-round foundation to a multi-round formulation, allowing the AI's uncertainty sets to adapt dynamically to the evolving conversational transcript. This enables the principled control of collaboration constraints throughout the entire dialogue rather than at a single point in time. Theoretical frameworks for human AI synergy. A broader literature seeks to formalize complementarity, where the joint system outperforms either agent alone. One line models this using Bayesian frameworks or taxonomies of collaboration modes 105562. Another analyzes how algorithmic outputs shape human decisions through strategic influence or noisy ranking models 222439. Our framework parts from these approaches in three ways. 1, we treat the human as a complete black box requiring no assumptions on behavior. 2, our guarantees are distribution-free and remain valid under arbitrary shifts in human behavior. And 3, we address multi-round dialogue rather than single-stage interactions. Theoretical and algorithmic multi-round collaboration. Multi-round collaboration is largely studied through agreement protocols aimed at reaching consensus or aggregating information. 1, 8, 19, 20, 27. Our framework differs in its assumptions. While these protocols require agents to communicate probabilistic beliefs or best response action, we treat the human as a black box who only provides a prediction set. Furthermore, while agreement protocols place the human and the AI on equal footing, we adopt a human-centered point of view. This ensures that the AI remains harmless and helpful to the human, regardless of whether the parties ever reach an agreement. 3, background. Single-round collaborative prediction sets. In this section, we review the key concepts, definitions, and structural results that arise in single-round human AI collaboration, which will serve as foundational building blocks for our multi-round setup. Consider a prediction problem with features x and labels y, drawn jointly from an unknown distribution p. The goal is to construct a prediction set cx that contains the true label A with high probability while remaining as small as possible. In the collaborative setting, a human expert and an AI system jointly construct the prediction set. For a given input s equals x, the human first proposes a set of plausible outcomes hxy, reflecting their proposal. The AI then refines this proposal and outputs a final prediction set cx equals cx hxy. From the AI's perspective, the human proposal is treated as a black box. The algorithm observes only the set hx, not how it was generated. To ensure collaboration is both trustworthy and beneficial, AI's refinement is required to satisfy two guiding principles. Counterfactual harm. The AI should not degrade correct human judgments. If the human's proposed set already contains the true label, the AI should preserve it with high probability. Formally, for user-defined epsilon 01, p, y set c, x, y, h, x, less or equal to epsilon 1. Complementarity. The AI should add value precisely when the human misses the correct outcome. If the true label is absent from the human proposal, the AI should recover it with high probability. For user-defined delta 01, p, y, c, x, y slash h, x, greater or equal to 1 minus delta 2. Not all prediction sets satisfying these requirements. The objective is to minimize accepted set size. Min c colon s right arrow 2 e c x free scp y slash c x y h x less or equal to epsilon p y c x y slash h x greater or equal to 1 minus delta, where epsilon delta 01 control the allowed levels of counterfactual harm and complementarity, respectively. A key result from 48 characterizes the optimal solution to this problem in the population setting. Theorem 3.1. The solution to the optimization problem 3 that minimizes ECX is of the form c asterisk x equals y colon sx y less asterisk 1 y slash hx plus b asterisk 1 y hx. Given this, several points follow. I to functions x, y is a nonconformity score, a standard notion in conformal prediction. Roman 2 in the single round framework of Norani et al. 48. The AI contributes only once at the end of each interaction. Consequently, the AI's behavior within a problem instance does not influence the human's proposal, and offline exchangeable calibration techniques remain applicable. This separation breaks down in the multi-round setting. Because the AI intervenes repeatedly within each interaction, its prediction sets to influence the human's subsequent behavior. As a result, human behavior evolves in response to the AI's actions, making offline calibration infeasible. For this reason, our analysis is entirely online. Roman 3. Despite these differences, we retain a key structural insight from Theorem 3.1. In the single round setting, the sets take the form SS, y less asterisk 1 y slash hx plus b asterisk 1 y hx, where the indicators 1 y slash hx and 1 y hx arise directly from the definitions in 1 and 2. As we will see in the next section, in the multi-round setting, counterfactual harm and complementarity become user-defined, and these indicators are therefore replaced by more general events defined over the interaction history. We now proceed to the formal problem formulation for multi-round human AI collaboration. For problem formulation, multi-round collaboration. In this section, we introduce an interaction protocol and a framework for user-defined requirements in multi-round human AI collaboration. 4.1 Interaction protocol. We propose a human AI interaction protocol in n-line where problems arrive sequentially over time and are handled one at a time. At each time step t equals 1 2, a new problem instance tariffs representing a task the human seeks to solve together with an unknown ground truth answer it y2. The correct answer it is unknown to both the human and the AI during the interaction. For each problem pt, the human and the AI engage in a multi-round dialogue. The interaction consists of n t n rounds where the stopping time n is chosen by the human. At high level, the human and the AI alternate between proposing candidate answer sets and exchanging textual messages after which the true answer is eventually revealed. Formally, for each date and rounder equals 1 nt, the human proposes a pair htr at r, where htr is a set of candidate answers and UTR is a textual message. The AI responds with a pair CTR at R, where CTR is a prediction set refining the human's proposal and it is a textual response. At the end of date, after the interaction terminates, the ground truth answer is revealed. The interaction protocol consists of 4 components: human textual messages at R, AI textual messages at R, human prediction sets HTR, and AI prediction sets CTR. Among these, our algorithmic focus is exclusively on designing the AI prediction sets. The remaining components are treated as black boxes. We make no assumptions about how human or AI textual behavior evolves, nor about how the human updates their prediction sets in response to the AI. We briefly argue why this modeling choice is both natural and useful. The textual components at R may depend arbitrarily on the full interaction history and may convey any information available to the respective party, such as clarifications, questions, intermediate reasoning, or external context. In particular, the AI's textual responses can be viewed as those of a fixed pre-trained language model capable of engaging in a dialogue. Treating these textual components as black boxes allows us to decouple language generation from uncertainty quantification and to remain agnostic to how computational behavior adapts to the interaction. 2. The label says it could itself be a function of 10R framework, but for simplicity we avoid introducing that notation. 5. While the textual components facilitate the flow of information between the two parties, the prediction sets play a distinct role. They represent each party's uncertainty about the ground truth answer, which is ultimately the most consequential quantity for decision-making and downstream action. Through principled communication of uncertainty via prediction sets, both parties can calibrate how much trust to place in each other's inputs, determining whether the collaboration is both harmless and productive. Accordingly, in the remainder of this paper, we focus on how the dynamics between the human sets HER and the AI sets CTR should be governed. From an algorithm design standpoint, we have no direct control over human behavior, and we therefore treat the human prediction sets as black box objects provided to the system. Therefore, our focus is exclusively on designing the AI's prediction sets. We now turn to the question of how the AI's prediction sets should be constrained so that they are maximally beneficial to humans in a multi-round setting. 4.2 User-defined collaboration requirements. In multi-round interactions, counterfactual harm and complementarity no longer admit a single canonical definition. Even when the high-level goal is clear, preserving correct human judgments and complementing incorrect ones, the precise operational meaning can vary across applications. Let us first focus on counterfactual harm. To gain intuition, fix a date around R greater or equal to 2. Consider the human transcriptive sets up to this point HE1:R equals HE1 HTR and the AI set at round R CTR it. From the perspective of defining a counterfactual harm requirement at round R, the high-level goal is to enforce that the AI includes the truth at this round, i.e. that 1 its CTR is likely conditional on an event indicating that the human had the truth in some meaningful sense. For instance, 1 y condition on -1 yt HTR, that is human included the truth at round R, -1 yt HTR HTR -1, that is human insisted on truth over the last 2 rounds so far, -1 r less or equal to R:(yt HTR, that is the human proposed the truth at least once. Any other conditions are possible. Different choices can lead to qualitatively different collaboration dynamics, including different AI set sizes. This motivates a general framework in which counterfactual harm is defined with respect to a user-specified rule, depending on users' preferences in different applications. Rule-based formulation. We formalize user-defined counterfactual harm through arrow a binary function that specifies when the counterfactual harm constraint is applied. Concretely, a counterfactual harm rule maps a label and a complete transcript prefix of human sets for the day and a round index to 01 RCH y HT1:NT R01, where HT1:NT equals HT1 HT denotes the full transcript prefix of human sets over all round of date, and R1 NT indexes the round under consideration. We interpret RCHY HT1:NT R equals 1 6 as the rule triggering at round rough date for the correct label. The examples above correspond to different choices of RCH, allowing the rule to depend on the full transcript HE1:N tells to capture rules that involve global properties of the interaction, such as whether round raised the terminal, round R equals NT, or whether the human ever included a label across the entire dialogue. Since rules are evaluated post-hoc after the interaction on day thus concluded and the ground truth is revealed, the full transcript is available at evaluation time. Given a rule, we say that counterfactual harm occurs on date if there exists a round in which the rule triggers but the AI fails to include the truth. At T equals next R1 NT RCH at HT1:NT R1 YT/CTR. Accordingly, the cumulative number of counterfactual harm violations up to time to T equals 1 at T. Similar construction applies to complementarity. We formalize user-defined complementarity requirements through a verifiable rule. Our comp y ht1 colon nt r 01, where r comp y ht1 colon nt r equals 1 indicates that if it were the correct label, the AI is required to include at round in order to complement the human's proposal. Given a complementarity rule, we say that a complementarity error occurs on day if there exists a round in which the rule triggers, but the AI fails to include the truth. E comp t equals max r1 ntr comp it ht1 colon nt r1 yt slash ctr. The cumulative number of complementarity failures up to time is then given by pt t equals 1 e comp t. The goal of multi-round human AI collaboration is to design the AI prediction set ctr so as to control counterfactual harm and complementarity errors over time. Concretely, for use specified tolerance epsilon delta 01, we seek to enforce the following constraints for all horizons t greater or equal to 1. 1 ttx t equals 1 edge t less or equal to epsilon and 1 ttx t equals 1 e comp t less or equal to delta 5 algorithm and guarantees. In this section, we present our online algorithm for multi-round human AI collaboration. Throughout this section, we follow the interaction protocol and assume two rule functions are c and r compare pre-specified by the user, all of which discussed in section 4. Recall that the rules are y ht1 colon nt r depend on the full transcript of human sets, which is only available after the interaction on day thoughts concluded. However, the AI must construct its prediction sets during the interaction at each round r before int is known. To handle this, at round rwe, evaluate each rule on the transcript prefix ht1 colon r, treating the current round as if it were the terminal round. Ry ht1 colon r colon equals ry ht1 colon r r. We refer to ROS the online activation of the rule r. 7. Exception 5.1 for each rule r rch r comp and its online activation r, we assume that ry ht1 colon nt r less ry ht1 colon r for all libs uy, all transcripts ht1 colon nt, and all rounds are less or equal to nt. Remark 5.1 Assumption 5.1 is a mild technical condition and is satisfied by a broad class of rules. All rules discussed in section 4.2 and instantiated in the experiment section 6 satisfy this assumption. Let us introduce the notion of a transcript. For each date and rounder, let ttr colon equals pt htj at j ctj at jr j equals 1. Denote the full transcript of the interaction up to round day t, including the problem instance, human and AI prediction sets, and their textual messages. We let s colon t times y right area 1 be a nonconformity score that assigns a real valued score to each label y. Given a transcript at date and rounder, the AI constructs its prediction set as ctr equals in yyt colon sttr y less tau t rch y ht1 colon r plus lambda r comp y ht1 colon ro. Here, the online activations rc and r comp determine which thresholds are active for a given label at round r, while the thresholds tau and lambda determine the strictness with which counterfactual harm and complementarity are enforced. Importantly, the thresholds tau and lambda are fixed throughout each date and therefore indexed only by t, that is, within a single problem instance tt. The same thresholds are used across all rounds, while the prediction set ctr would still evolve with ROS. The transcript grows and the score value as ttr change. We discuss concrete choices of the score functions for our applications in section 6. Under this parameterization, the problem of designing AI prediction sets reduces to the problem of calibrating the daily thresholds tau lambda online so as to control the cumulative counterfactual harm and complementarity errors. The thresholds are updated at the end of each day. Once the ground truth label is revealed and the error indicator CCH 10 comp t can be evaluated. Specifically for step size eta 0 and target. Let us epsilon delta 01. The thresholds are updated according to tau plus 1 equals max 0 tau plus eta at t minus epsilon lambda plus 1 equals max 0 lambda t plus eta e comp t minus delta o. The next 0 operator can be interpreted as a projection step that ensures the thresholds remain non-negative. This projection is needed to handle some degenerate cases in proof of theorem 5.2, which provides the error control guarantees. The update rule itself follows a standard approach for online tracking of quantiles. Intuitively, whenever the observed error exceeds its target level, the corresponding threshold is increased to make future prediction sets more conservative. When the error falls below the target, the threshold is decreased. As the following theorem shows, this simple update suffices to control cumulative counterfactual harm and complementarity errors in the online setting. 8. Theorem 5.2 finite simple online control of collaboration errors. Under assumption 5.1 and assuming tau 1 equals lambda 1 equals 0 and step size eta 0, then for every horizon t greater or equal to 1, ttx t equals 1 h t less or equal to epsilon plus 1 plus eta t1 ttx t equals 1 e comp t less or equal to delta plus 1 plus eta t. Theorem 5.2 shows that our algorithm achieves finite simple control of both counterfactual harm and complementarity, thereby enforcing user-defined constraints on the collaboration dynamics. Importantly, these guarantees hold in a fully online and distribution-free manner, without any assumptions on the distribution of problems, the human's behavior, or the internal mechanisms of the AI system. 6 experiments. We evaluate our framework in 2 interactive settings: LLM simulated agents for scalable verification and human crowdsourcing for real-world validation. Our objective is twofold. First, we verify that our online algorithm strictly adheres to nominal targets epsilon and delta under non-stationary conditions. We then validate the utility of our organizing principles by showing that counterfactual harm and complementarity are the right metrics to control from the AI side. While we cannot directly dictate human behavior, we find that enforcing these human-centric rules translates to predictable and desirable changes in the human's final decision quality. By varying the strictness of these guarantees, we demonstrate that these two notions are not just mathematical abstractions but are the fundamental levers required to steer human judgment toward better outcomes. Specifically, by algorithmically regulating the AI's uncertainty, we protect humans from abandoning correct intuitions and help them recover correct answers they initially miss. Instantiation of rules and score functions. To instantiate the general framework, each experiment specifies a pair of verifiable rules rch r comp is in section 4.2 and Roman 2a nonconformity score sttr y01 section 5. The rules used across both settings are defined as follows. For a label and a transcript history GTR, the counterfactual harm rule is triggered at any round where the human's latest prediction set already contains the true label rchy ht1 colon nt r equals 1 wide htr. Since this rule depends only on the current round, its online activation coincides with the rule itself rchy ht1 colon r equals 1 wide htr. The complementarity rule triggers only at the final round and if the human's final proposal lacks the label r comp y ht1 colon nt r equals 1 y slash htr when r equals nt. These rules ensure that ECH t monitors whether the AI fails to include the ground truth the human already considered at any point, while ecomp t monitors whether the AI fails to provide the ground truth in the final round when the human is missing it. In both experiments, the AI agents are powered by LLMs that provide probability vectors pt r y01 over the label space condition on the transcript ttr. To ensure these values constitute a valid probability distribution and to mitigate the impact of LLM hallucinations, we normalize the raw model outputs across the label space. From these normalized probabilities, we derive the standard nonconformity score sttr y colon equals 1 minus pt r y. 9. 6.1 LLM simulated experiments. To evaluate our framework at scale, we first simulate human AI collaboration using LLMs as proxy agents to model human-like decision-making in a controlled environment. 3. Enabling large-scale, reproducible tests of multi-round dialogue dynamics. Experimental design. Medical diagnosis. We utilize the DDX plus dataset 66, which consists of synthetic patient records including demographics, symptoms, and ground truth diagnosis. Each date corresponds to one patient case each with ground truth diagnosis ct. To ensure collaboration is functionally necessary, we introduce a structural information asymmetry. The human agent GPT-4o mini observes demographics and a small set of initial symptoms, while the AI agent DeepSeek Chat observes a complementary subset of diagnostic evidence but is blind. The demographics. The interaction unfolds through a dynamic dialogue where the human maintains a fixed-size candidate set of 2 diagnoses. In each round, the human proposes uses a set HT-rand A textual message at R, to which the AI responds with a refined prediction set CT-rand its own textual feedback at R. Following each AI response, the human agent evaluates the new information to decide whether to update their prediction set, request further clarification, or terminate the session. Once the interaction concludes either by the human's choice or upon reaching a round limit, the human provides a final assessment set. This final set captures the human's ultimate judgment following the dialogue, allowing us to evaluate how effectively the AI's uncertainty communication steered the human toward the correct diagnosis. The empirical convergence. Figure 12 reports the running averages of the realized errors DCH, T, and ECOM, T for a representative target pair. Consistent with theorem 5.2, the observed averages stabilize near their nominal targets despite the fact that the human agent's dialogue policy, sudden times and T, and set updates are unconstrained and may vary across trials. Additional settings appear. Appendix C. Figure 1. Empirical convergence of error rates in the LLM simulated medical test for complementarity left and counterfactual harm right. Both plots track the cumulative average running error. AVD error equals 1. TBD I equals 11 error I over sequential trials 10. From AI sets to human decisions, having established that we can control these measures, we evaluate whether they are meaningful proxies for collaboration quality. By running multiple instances of our algorithm with varying error targets, we observe how the complementarity and counterfactual harm constraints influence the human's final decisions. As illustrated in Figure 2, we observe a direct correlation between the AI's error targets and human outcomes. Figure 2. Human decision outcomes across varying AI error targets in the LLM simulated medical test. Left, human GT gain rate as a function of the complementarity error target epsilon comp. Right, rate of abandoning a correct initial guess GT loss is a function of the counterfactual harm error target epsilon CH. Specifically, when we increasing the allowed counterfactual harm CH results in participants frequently abandoning correct initial guesses. This happens when the AI set excludes the true label, inducing the human to discard their correct judgment. Conversely, tightening complementarity comp increases the recovery rate, the frequency with which participants identify the correct label after an initial error. In these cases, the AI set includes the missed label, which the human then adopts. These results demonstrate that CH and comp are the fundamental levers of collaboration. By regulating these two metrics in the AI's prediction sets, we achieve predictable improvement in human decisions without the need to model or control human behavior directly. 6.2 Crowdsourcing experiment. Collaborative shape content. While LLM simulations provide a saleable testbed for our algorithm, they cannot fully capture the nuances of human trust fatigue or heuristic-driven reasoning. We therefore conduct a human crowdsourcing study to test our framework's real-world robustness. Specifically, we evaluate whether enforcing CH and comp constraints strictly on the AI's prediction sets reliably improves human decisions and confirming that these principles remain effective when interacting with unpredictable human participants. Test design. We evaluate our framework using a collaborative visual reasoning test where participants work with an AI assistant to estimate the count of target shapes, for example triangles, squares, or stars within a cluttered image. Each trial begins with the human viewing an image for 1 second before providing an initial guess as a contiguous range of 3 integers. This fixed set size is maintained for humans proposals throughout the interaction. To facilitate collaboration, an AI assistant, powered by a Gemini 2.5 Flash Model 28, analyzes a noisy version of the image to produce a distribution over counts, which our algorithm converts into a prediction set for the human. The interaction then enters a second round where the human reviews the image for 0.5 seconds, observes the AI set, and revises their guess. The AI then updates its distribution given the computation history and provides a final set. The interaction concludes with the human submitting a final assessment based on the dialogue. Appendix C provides full interface and parameter details. Epsilon CH, epsilon comp, table 1 algorithm instantiations. Target rates for counterfactual harm. CH and complementarity comp. We instantiate 3 AI assistants, each running our algo, with them with different target error rates for counterfactual harm and complementarity. Algorithms A and B share the same complementarity target, but differing counterfactual harm. Algorithms A and C share the same counterfactual harm target, but differing complementarity. We ran our study via prolific free involving 1,000 total interactions across 50 participants who arrived sequentially. Each participant was randomly assigned to one of 3 algorithms and completed 20 trials. For each algorithm, we tracked the calibration state globally across all users in a single stream, updating thresholds continuously as new participants joined. This design creates significant non-stationarity due to variations in individual accuracy, speed, and trust, providing a rigorous real-world stress test for our online distribution-free guarantees. Empirical convergence. Despite the shifting human dynamics, Figure 3 shows that our algorithm successfully adapted its thresholds to maintain target error rates across the entire population. Additional convergence results for the other instantiations can be found in Appendix C. Downstream results. From AI errors to human decisions, we now evaluate how the algorithm's adherence to counterfactual harm CH and complementary comp target shapes actual human outcomes. To isolate these effects, participants were required to maintain a fixed set size of 3 integers for their guesses throughout the trial. This constraint is critical. It ensures that changes in human accuracy are driven specifically by the AI suggestions rather than fluctuations in the human's own uncertainty or set size efficiency. Theme 1. Direct impact of AI errors on human behavior. To determine if CH and comp serve as effective proxies for collaboration quality, we analyzed trials where these rules were triggered and measured how AI errors alter human outcomes. We specifically examined whether preventing harm preserves correct human answers by focusing on trials where the human initially held the ground truth GT. As shown in Figure 4 top row, a CH error significantly increases the rate at which humans abandon the correct answer. In algorithm A, for example, the GT loss rate rises from 5.8% to 28.6% when a CH error occurs. This demonstrates 3 https://www.prolific.co/12. Figure 3. Error convergence for algorithm B in the crowdsourcing study. Both plots track the cumulative average running error. AVD error equals 1. TPT I equals 11 error I, where observed rates for counterfactual harm left and complementarity rates stabilize at their nominal values. At AI failures to reinforce correct human beliefs can directly induce humans to discard their initial strengths. We also examined whether AI complementarity directly aids human recovery by focusing on trials where the human initially left the ground truth GT. We partitioned these cases by whether the AI provided the GT or committed a comp error. The results in Figure 4 bottom row show that successful AI complementarity leads to significantly high recovery rates in humans. In algorithm B, for instance, humans identified the GT in 35.8% of trials when the AI was complementary compared to just 3.1% when the AI failed to include it. This gap confirms that providing the missing label in the prediction set is the primary mechanism for helping humans overcome initial errors. Theme 2. Comparative impact of algorithmic guarantees. Beyond the per error analysis above, consistent with our LLM simulations, we compare different algorithm instances to demonstrate how shifting the counterfactual harm and complementarity error targets globally influence human performance. Comparing algorithm B's loser counterfactual harm guarantee against algorithm A's stricter target, we observe a clear correlation. As the AI is permitted to commit more CH errors, participants become significantly more likely to abandon the previously held ground truth. Figure 5a. A similar trend emerges when comparing the complementarity targets of algorithms A and C. Figure 5b. We find that a stricter complementarity guarantee directly increases the human recovery rate because the human set size remains fixed at 3. These shifts in coverage cannot be attributed to changes in set size efficiency. Instead, these results confirm that counterfactual harm and complementarity are the primary levers of the interaction. By precisely adjusting the target rates for these two error types, we can predictably steer the final decision quality of a human partner without needing to model their individual behavior or latent trust levels. 13. ALDA CH, BLBCH, CLCCH, DLBCOM, ELBCOM, FLCCOM. Figure 4. Behavioral impact of AI errors in the crowdsourcing test across algorithms A, B, and C. Top row colon human GT loss rates compared across trials with and without CH errors. Bottom row. Human GT gain rates compared across trials with and without comp errors. CH, ALDA vs LB, BCOM, ALDA vs LC. Figure 5 colon impact of nominal error rates on human outcomes. Comparison of humans. GT loss rates between algorithm epsilon set H equals 0.05 and algorithm B epsilon set H equals 0.30. B comparison of humans GT gain rates between algorithm epsilon comp equals 0.50 and algorithm C epsilon comp equals 0.7. 14. 7. Discussion and future work. We introduced a multi-down human-AI interaction protocol, a rule-based framework for specifying user-defined constraints over collaboration dynamics, and an online algorithm with finite sample guarantees that provably enforces these constraints over a sequence of computations. A key limitation is that we control collaboration dynamics by constraining the A prediction sets, which represent only one mechanism for communicating uncertainty in settings where outputs are open-ended or do not lie in a well-structured candidate space. Other uncertainty representations may be more appropriate. Extending our rule-based control framework and online guarantees to alternative uncertainty objects is a promising direction for future work. References 1 Arons and Ness. The Complexity of Agreement 2004. URL https://arxiv.org/m/cs/0406061. 2 Adderall and Brown W. Diversified recommendations for agents with adaptive preferences 2022. URL https://arxiv.org/m/2010.07773. 3 out D. Rada R. I and Kali A. T. Using large language models to simulate multiple humans and replicate human subject studies 2023. URL https://arxiv.org/m/2010.10264. 4 Angel Bulas A. Bates S. Alec J. and Jordan M. I. Uncertainty sets for image classifiers using conformal prediction 2022. URL https://arxiv.org/m/2009.14193. 5 Angel Bulas A. N. Barbara R. F. and Bates S. Online conformal prediction with King. Set sizes 2024. URL https://arxiv.org/m/25402.01139. 6 Angel Bulas A. N. Bates S. Fish A. Light Ellen Chester Key. Conformal risk control 2025. URL https://arxiv.org/m/2202.8.14. 7 Arnes Rodriguez A. Pence N. C. The Jess V.S. Oliver N. and Gomez Rodriguez M. Towards Human AI Complementarity in Imagine Tests 2025. URL https://arxiv.org/m/2008. 13285. Edelman R. J. Agreeing to disagree. The Annals of Statistics 46 12836112839. November 1976. Doi 10.1214 ausnischen Befund 76 43 254. URL https://doi.org/10.121/house/1,176,343,654. 9 Bebar V. Bet U and Wo A. On the utility of prediction sets in human AI teams 2022. URL https://arxiv.org/m/2005.01411. 10 Benzel G. Mishi B. Tamer E. Horvitz E. and Weld D. S. Is the most accurate AI the best teammate? Optimize AI for teamwork 2021. URL https://arxiv.org/m/254.13102. 11 Bethany H. Harsha P. Pradis G. and Singvi D. Learning personalized product recommendations with customer disengagement. Manufacturing and service operations management 24 12 2021 doi 10.1287/and/some.2021147. 12 Ben Sen L. C. and Rodriguez M. D. Human alignment influences the utility of AI assisted decision making 2025. URL https://arxiv.org/m/25500.14035. 15. 13 Battener A. Wang H. Chen Xian by Y. Approved online conformal prediction vibe. Strongly adaptive online learning 2023. URL https://arxiv.org/m/200302.07869. 14 Bort S. and von Luxburg U. A bandit model for human machine decision making with private information and opacity. Encapsulates G. Ruiz F. J. R. and Voa I. Eds. Proceedings of the 25th International Conference on Artificial Intelligence and 66. Volume 1 and 951. Proceedings of Machine Learning Research pp. 7319. PNLR 2830 Mar 2022. URL https://proceedings.mlr.press/v151/422a.html. 15 Cadets at F. Kempedner and Somfins at L. M. Studying Human AI Collaboration Protocols. The case of the Kasparov's law and radiological double reading. Health Information Science and Systems 91:8. February 21 doi 10.1 p 7 s13 and 5 to 21 to p 38 16 Chen L. Havilman LD. Trinivasa S. and Dryden A. The Assistive Multi-Armed Bandit 2019. URL https://arxiv.org/m/19 17 MA. Mazanar H. Sandak D. and Sanadi S. Sample Efficient Learning of Predictors that Complement Humans 2022. URL https://arxiv.org/m/2202.99584. 18 Chen B. Lao Q. V. Von J. W. and Benzel D. Understanding the Role of Human Intuition on Reliance in Human AI Decision Making with Explanations 2023. URL https://arxiv.org/m/21301.07255. 19 Kalina N. Globaceris I. Goal S. Pippa V. Roth and G. M. Collaborative Prediction. Trackable Information Aggregation via Agreement pp. 4 and 12 4 and 98 doi 10.11378 1.978 161 1978971 172. URL https://ivas.sam.org/10.1137/1.978 161 20 Kalina N. Goal S. Gupta V. and Roth A. Trackable Agreement Protocols and Proceedings of the 57th Annual ACM Symposium on Theory of Computing. Stock 25 pp. 532 543. New York, NY, USA 2025. Association for Computing Machinery. ISD 9,098,4 families and 9.195 10.145 EFN 17.823.3782222. URL https://doi.org/10.11457,717,823.3718222. 21 Courts Gomez S. Patinho C. Byland Y. Wu S. Horvitz E. and Wilder B. Utility Directed Conformal Prediction. A Decision Aware Framework for Actionable Uncertainty Quantification 2025. URL https://arxiv.org/m/2477. 22 Cavell B. and Stevenson M. T. Algorithmic Civil Engineering. Papers and Proceedings 11096 100. May 2020. 10.125/pamp.20201037 URL https://www.elub.org/articles = 10.125/pamp.20201037 23 DRD.m Fabiato R. and Chuchovate. Case for humans in the loop. Decisions in the presence of erroneous algorithmic scores in proceedings of the 2020 CHI Conference on Human Factors in Computing Systems CHI 20 pp. 112 Atom April 2020 doi 10.1145/3,313,833.7668 URL http://10.1145/3,313,831.3376638 24 Donahue K. Gall Beauty S. and Collies K. When are two lists better than one? Benefits and harms in joint decision making 2024 URL https://archive.org/web/2308.11721 25 Fabiato R. Chapity S. Lundgren M. Fitze M. Parkinson M. Wilson D. Fisher P. Horvitz E. Inkman K. and Nishi B. Who goes first? Influences of human AI workflow on decision making in clinical imaging 2022 URL https://archive.org/web/2205.09696 16 26 Gao Q 2 W Han H Shen M and Gao D Human Centered Human AI Collaboration H Check 2025 URL https://archive.org/web/2500.5.22477 27 Gene Koplos J D M Polmar Chatis H M We Can't Disagree Forever. Journal of Economic Theory 28.1:192 This is the 22.2 doi https://doi.org/10.10 90,099-0 URL https://www.science.direct.com/science/article/fita/22053182900990 28 Gemini Team Google Gemini a family of highly capable multimodal models. RZIF for print RZIF 23.12.11805 2024 URL https://archive.org/web/2312.11805 29 Gibbs Ian Kens E J Conformal inference for online prediction with arbitrary distribution shifts. Journal of Machine Learning Research 05162:136 21124 URL http://gmlr.org/paper/v25/22-1218.html 30 Gibbs Ian Kens E Adaptive Conformal Inference under Distribution Shift 2021 URL https://archive.org/web/2001.3 31 Hammer P Feed L Versing M Jakubik J and Cool N Learning to Defer with Limited Expert Predictions 2023 URL https://archive.org/web/2304.07306 32 Vu X Undo D D Sliffins N Wu Z S Incentivizing Combinatorial Bandit Exploration 2022 URL https://archive.org/web/2206.00494 33 Holman J Wu Y Psi D Guo D and Gentleman A Conformal Prediction and Human Decision Making 2025 URL https://archive.org/web/2500.3.11709 34 More than Now J Sliffins N Wu Z S Incentivizing Exploration with Selective Data Disclosure 2024 URL https://archive.org/web/1811.06026 35 Canvas Q&SM Origis and J Hi M Roth A Thor R and Wu Z S Furnace Incentives for My Ob Agents 2017 URL https://archive.org/web/1705.02321 36 Stefani B Lees M and Kentpati K Towards Unbiased and Accurate Deferral to Multiple Experts 2021 URL https://archive.org/web/2102.13004 37 Gianni S Habis G and Hassani H Length Optimization and Conformal Prediction 2024 URL https://archive.org/web/2404.3881 38 Gianni S Habis G Roth and Hassani H Decision Theoretic Foundations for Conformal Prediction Optimal Uncertainty Quantification for Risk Averse Agents 2025 URL https://archive.org/web/22500.22561 39 Kleinberg J and Rega Van M Derivative Monoculture and Civil Welfare. Proceedings of the National Academy of Sciences 1 B 1822 Bay 2021 is in 1,091 find doi 10.1073 Safe Penis 2,018,340,001 D 18 URL http://ddex.doi.org/10.1073/penis.20.8340.18 40 Lay J G Cell M Renato A Tidrani R J and Washman L Distribution Free Predictive Inference for Regression 2017 URL https://archive.org/web/1604.04173 41 Lucky Fact J Angel Bulas A N Batch C A Jordan M Ian Malik J Conformal Decision Theory Thief Autonomous Decisions from Imperfect Predictions 2024 URL https://archive.org/web/213.05921 17 42 Lindemann L Del Y UX Habis G J and Desmond J V Formal Verification and Control with Conformal Prediction 2025 URL https://archive.org/web/2409.00536 43 Madras D Fidacy T and Zemel R Predict responsibly improving fairness and accuracy by learning to divert 2018 URL https://archive.org/web/1711.06664 44 McLaughlin B and C J Algorithmic Assistance with Recommendation Dependent Prefer Says 2025 URL https://archive.org/web/2208.07626 45 Mazanar H and Santet D Consistent Estimators for Learning to Defer to an Expert 2021 URL https://archive.org/web/2006.01862 46 Mazanar H Benzel G Forney and Horvitz E When to Show a Suggestion Integrating Human Feedback and AI Assisted Programming 2024 URL https://archive.org/web/2306.04930 47 Norani S Kiani S Habis G and Hassani H Conformal Prediction Beyond the Scene A Missing Mass Perspective for Uncertainty Quantification in Generative Models 2025 URL https://archive.org/web/22500.05497 48 Norani S Kiani S Habis G and Hassani H Human AI Collaborative Uncertainty Quantification.RZIF for print RZIF:10.23476 2025 49 Norani S Romero O Ebro N D Hassani H and Pappas D J Conformal Risk Minimization with Variance Reduction 2025 URL https://archive.org/web/2411.01696 5th Cuddy and Gomez Rodriguez M Differentiable Learning Under Triage 2021 URL https://archive.org/web/103.08902 51 Papadopoulos H Prodrup K Log B and Garin A Inductive Confidence Machines for Regression in Machine Learning ECMO 2002 13th European Conference on Machine Learning Helsinki Finland August 1923 2002 Proceedings 13 pp 345 356 Schrader 2002 52 Quetch V Fish A Chester T LA Son J H Jacola T S and Barsley R Conformal Language Modeling 2024 URL https://archive.org/ab/2306.1019 53 Red Who M Bloomer K Prado G Plainberg J Obermeyer D and Melanathan S The Algorithmic Automation Problem Prediction Triage and Human Effort 2019 URL https://archive.org/ab/19 3.12220 54 Remlingam R Kiani S and Roth A The Relationship Between Norgret Learning and Online Conformal Prediction 2025 URL https://archive.org/ab/2502.109447 55 Resto BC Liddy L Holstein K and Tidari H A Taxonomy of Human and ML Strengths in Decision Making to Investigate Human ML Complementarity 2023 URL https://archive.org/ab/1 56 Romano Y Patterson E and Kensky J Conformalized Quantile Regression 2019 URL https://archive.org/ab/19 5.03222 57 Romano Y CJ M and Kens E J Classification with FUD and Adaptive Coverage 2020 URL https://archive.org/ab/2006.025544 58 Sentinel M J and Wasserman L List of BUS set value classifiers with bounded error levels. Journal of the American Statistical Association 1.14 plan 25:232 34 2019 18 59 Saunders C. Dameron and Vok B. Transaction with Confidence and Credibility in Proceedings of the 16th International Joint Conference on Artificial Intelligence Volume 2 AK 99 pp. 722-726 San Francisco CA USA 1999 Morgan Kaufman Publishers Inc. 60 Saunders C. Dameron and Vok B. Transaction with Confidence and Credibility 1999 61 Chevet H and 2 Geek J. W. Non-parametric estimation I validation of order statistics. Analysis of mathematical statistics 16:2:1 E 7192 Jan 1945 doi 10.1214 AOM and BIF 177 fan 31 URL https://doi.org/10.1214 AOM and BIF 177 MIF 731,100 62 Stivers M. Tishida H. Carden G. and Smith P. Bayesian Modeling of Human AI Complementarity. Proceedings of the National Academy of Sciences 1911 E2 billion 11 myth 547,019 2022 doi 10.1073/penis.21115471119 URL https://www.penis.org/doi/10.1073/penis 2 biv 1 11 myth 547,019 63 Stratery E. Wengel Akati N. and Rodriguez M. T. Improving Expert Predictions with Conformal Prediction 2023 URL https://archive.org/ab/2200 64 Stratery E. The Desuit S. and Rodriguez M. T. Controlling Counterfactual Harm and Decision Support Systems Based on Prediction Sets 2024 URL https://archive.org/ab/2406.06671 65 Stitz D. Krishnamurti D. Vijayam Central A. D. and Desert A. Learning Optimal Conformal Classifiers 2022 URL https://archive.org/ab/2110.099192 66 T. Chengo A. F. Golar 1 T. Bartle J. and Guzan J. DD Excludes a new dataset for automatic medical diagnosis 2022 URL https://archive.org/ab/2005.09148 67 T. and R. Tamizuka M. Brett and A. D. and Betsy A. Towards Modeling and Influencing the Dynamics of Human Learning in Proceedings of the 2023 ACM/IEDE International Conference on Human Robot Interaction HRY 23 pp 350-358 New York NY USA 2023 Association for Computing Machinery ISBN 9 E1 B45 9 10.1145 CUE fan 68 62.3578629 URL https://org/10.1145 CUE fan 68 62.3578629 68 Tony G D Akadian The Jeslias Stratery E and Gomez Rodriguez M Towards Human AI Complementarity with Prediction Sets 2024 URL https://archive.org/ab/23405.17544 69 Vataro M Omadok and Malone T. When combinations of humans and AI are useful, a systematic review and meta-analysis. Nature Human Behavior 8:2002 and 93 2303 2024 doi 10.038 is for you Y62 024 02024 URL https://10.1038/S41562.024.02024 70 H. Yerkem Grand McLaughlin M. Gerstenberg T. Burstein M. and Krishna R. Explanations can reduce over-reliance on AI systems during decision making 2023 URL https://archive.org/ab/2012.06823 71 Verma R. and Nelznik E. Calibrated Learning to Defer with 1B as all classifiers 2022 URL https://archive.org/ab/2002.03673 72 Vov B. Theron and Saunders C. Machine Learning Applications of Algorithmic Randomness 1999 73 Vov B. Theron and Schaefer D. Algorithmic Learning in a Random World Volume 29 Ferner 2005 19 74 Wang L. Joachim T. and Rodriguez M. T. Improving Screening Process by Calibrated Subset Selection.archive F/2002 2.01147 2022 URL https://api.semanticscode.org/corpus ID :2 4 73,291 75 Wilder B. Horvitz E. and Kemmer E. Learning to Complement Humans in Proceedings of the 29th International Joint Conference on Artificial Intelligence AK 2021 ISBN 9,789,9 76 Wilkes S. Determination of Sample Sizes for Setting Tolerance Limits. The Annals of Math Agel 66 12 1:9196 1941 77 Yao F. Lizy Nikotlov D. Link H. and Zu H. How about his top recommendation under competing content creators 2023 URL https://archive.org/ab/200302.01971 20 Appendix Table of Contents Approves 22 Beat Extended Related Works 23 C Crowdsourcing Study Details and Interface 26 C.1 Participant Recruitment and Study Protocol 26 C.2 Image Generation and Difficulty Levels 27 C.3 User Interface 27 DLLM Simulated Experiment Details 28 E Extended Experimental Results 33 E.1 Extended Crowdsourcing Convergence Results 33 E.2 Extended LLM Simulation Convergence Results 33 21 Approves proof of theorem 5.2. We prove the counterfactual harm bound. The complementarity bound follows by the same argument with the substitutions tau t, h, t, epsilon 7 right lambda t, ecom t delta. Step 1. Relating tau t plus 1 to cumulative counterfactual harm dot by the update rule and the fact that max 0 greater or equal to 4 LR. We have for every tau plus 1 equals mass 0, tau plus eta h t minus epsilon greater or equal to tau t plus eta h t minus epsilon. Sign over it equals 1 10 tau so yields tau t plus 1 minus tau 1 greater or equal to eta tx t equals 1 h t minus epsilon, or equivalently tx t equals 1 h t less or equal to epsilon t plus tau t plus 1 minus tau 1 eta. 4. Step 2. Uniform upper bound on tau dot. We claim that tau less or equal to 1 plus eta for all t greater or equal to 1 when tau 1 equals 0. Tau greater or equal to 1, then ECH t equals 0. Indeed, whenever RCH at HT1 colon R equals 1, we have tau RCH at HT1 colon R plus lambda t R comp at HT1 colon R greater tau t greater or equal to 1, since lambda greater or equal to 0 by construction, because ST and R is 0 1. This implies that CT at every round where RCH equals 1, since RCH at HT1 colon NT R less RCH at HT1 colon R. This holds in particular at every round where the rule triggers, hence that t equals max R1 and TRCH at HT1 colon NT R1 YT slot TTR equals 0. Therefore, if t greater or equal to 1, then the update satisfies tau plus 1 equals max 0, tau t minus eta epsilon less or equal to tau t. So tau cannot increase while above 1. If it's tau t1, then ECH t less or equal to 1, and thus tau plus 1 equals max 0, tau plus eta h t minus epsilon less or equal to tau plus eta 1 plus eta. Combining the two cases yields tau t less or equal to 1 plus eta for alt, and in particular tau t plus 1 less or equal to 1 plus eta. Step 3. Concluding the finite sample bound dot plotting tau 1 equals 0, then tau t plus 1 less or equal to 1 plus eta into 4 gives tx t equals 1 h t less or equal to epsilon t plus 1 plus eta. Eta. Dividing by t proves 1 t dx t equals 1 h t less or equal to epsilon plus 1 plus eta. Eta t. The complementary bound follows identically. 22. Beat extended related works. Conformal prediction. Modern conformal prediction 5960 72 73 builds on the classical work on tolerance regions in statistics 61 76 to provide distribution-free finite sample validity for prediction sets. Over the past 2 decades, CP has become a standard tool in machine learning and classification, regression, and recently large language models for 6, 40, 47, 51, 52, 56, 57. There is a growing body of work with the aim to improve different aspects of conformal prediction, including length efficiency of the prediction sets 37, 49, 58, 65, online guarantees 5, 13, 29, 30, 54, and extension to decision theoretic frameworks 21, 38, 41, 42. Particularly, the decision theoretic angle supports the hypothesis that prediction sets, specifically with guarantees accompanied by conformal prediction, are a useful tool for human AI collaboration in high-stakes applications where reliable uncertainty estimates are essential for enabling trust and communication. Prediction sets for human AI decision support. A recent growing body of work considers prediction sets as a structured interface for collaboration and human decision-making support. 63. Formalizes how conformal prediction sets can improve expert prediction and multi-class classification. 12. Propose human-aligned calibration over standard calibration, which they argue ensures that AI-generated prediction sets are calibrated specifically on instances where human is likely to be incorrect. 9. Empirically evaluate sets as a form of advice in human AI sets and show that sets can improve accuracy compared to single-label predictions. 33. Analyze CP from a decision-theoretic perspective and examine tensions between coverage guarantees and decision-relevant uncertainty. 64. Analyze prediction sets-based decision support through the lens of counterfactual harm and formalize the concerns that requiring humans to select from machine-provided sets may degrade performance. 68. Propose a greedy algorithm to construct prediction sets that empirically improve human accuracy compared to standard conformal prediction sets. 74. Study calibrated subset selection and propose a distribution-free procedure that improves upon standard calibration by producing near-optimal shortlists with a target expected number of qualified candidates. These works study how humans use AI-generated sets to reach final judgments. The human is the end decision-maker receiving a single set. Our framework, following 48, incorporated the human input and treats the prediction set itself as the collaborative output where the human proposes a set and the AI refines it. Moreover, these works analyze single interactions per instance, leaving open how to handle iterative refinement across multiple rounds where the human may update beliefs, ask clarifying questions, or revise proposals. Agreement protocols formalize multi-round collaboration as iterative belief, exchange until consensus. The foundational result is Almond's agreement theorem 8, which states that two perfectly informed Bayesians with a common prior, different observations, and common knowledge of each other's posteriors must share the same posterior. Subsequent work is given finite time convergence protocols through which the different parties engage in a conversation about their beliefs about the outcome. 127. Recent work 20 generalized prior results and introduced trackable agreement protocols that replace Bayesian rational common assumption and earlier formulations with statistically efficient calibration condition that enables agreement theorems without distributional assumptions. 19. Extend upon these protocols and achieve information aggregation as well as in the setting where the two agents have asymmetric information. Our framework differs from agreement protocols in both interface and objective. First, these protocols require both agents to maintain and communicate probabilistic beliefs or expected values. Our setting 23. Requires only that the human provide a prediction set with no probabilities attached. Set. Agreement protocols focus on belief convergence and information aggregation. The goal is for agents to reach consensus. We prioritize different objectives, ensuring the AI's output does not harm correct human judgments, counterfactual harm while complementing incorrect one's complementarity. These objectives do not reduce to reaching consensus and require fundamentally different algorithmic machinery. Learning to defer. Another related area is learning to defer L2D, where an algorithmic tool learns when to defer a final decision to an expert human. Early work by 43 framed this is a mixture of experts problem, jointly training a classifier with a deferral mechanism. 45 extended this with a decision theoretic formulation, training models to complement human strengths rather than maximize accuracy alone. 71 showed that standard training objectives can fail to produce optimal deferral policies and proposed consistent surrogate losses guaranteeing Bayes optimal deferral. 53 frame automation is an instance-level triage problem and optimally assigning cases to humans. BS algorithms based on estimates of their respective errors. Extensions address various settings. 3136 study deferral with multiple experts, while 75 emphasize that humans and models are not independent and introduced dependent Bayes optimality to exploit correlations. 50 formulate differentiable learning under triage with exact optimality guarantees. 17 propose training-free deferral using conformal prediction to allocate decisions among experts. Most recently, 7 introduced collaborative matching for selective deferral. The L2D literature primarily asks who should decide on a given instance, the model or the human. These methods improve performance through selective abstention, which is fundamentally different from our objective. We do not focus on task allocation. Instead, we focus on joint decision-making. From a human-centric perspective, our work addresses how the AI should incorporate human feedback to build a prediction set that reflects the strengths of both parties, while L2D determines what collaboration should occur. Our framework governs how the collaboration proceeds once it has begun unfolding over multiple rounds. Theoretical frameworks for human AI complementarity. The concept of human AI complementarity where a joint system surpasses the capabilities of either agent in isolation has been a central focus of recent literature and provided a formal grounding for the synergy, investigating the specific team dynamics that enable AI to add value beyond standalone accuracy. Other researchers have approached this through a Bayesian lens, identifying the criteria under which collective belief updating leads to superior outcomes. 62. This has led to broad taxonomies that categorize how human cognitive intuition and machine learning precision can be optimally fused across different collaborative tests. 55. Despite these theoretical frameworks, empirical results suggest that achieving such synergy is non-trivial. 69 highlights a persistent app where human AI dyads often fail to outperform the more capable individual agent, even though they typically exceed baseline human performance. A second research thread examines how algorithms actively shape human choices through ranking and recommendations, while 22 analyze the strategic impact of recommendations on decision makers. Others have utilized the Miles model to study the interplay between algorithmic outputs and human preferences. 24. 39. More recently, human AI collaboration has been framed as a sequential learning problem. 16. 24. Introduce the assistive multi-armed bandit, where a robot learns to aid a human agent who is themselves discovering task rewards. Similar two-player perspectives are explored by 14, who emphasize the challenges of private information and audacity in shared decision tests. In recommendation systems, work by 2 and 77 explores how menu selection and creator competition influence users with adaptive preferences or random utility models. Furthermore, 67 and 26 represent a shift toward modeling the internal dynamics of human learning and human-centered collaboration, treating the human as a teammate whose mental state evolves over time. Our work departs from the above paradigms in 3 fundamental ways. Existing models typically rely on parametric assumptions such as Bayesian updates, malus noise, or specific internal mental models. In contrast, we treat the human as a complete black box. We make no assumptions about the human's rationality, learning speed, or internal state. Roman 2 our guarantees are distribution-free. Using online collaboration, we ensure that our collaboration constraints remain valid even under arbitrary, non-stationary shifts in human behavior or problem distributions. Roman 3 lastly, different from prior works that focus on reconciling symmetric agents, we adopt an asymmetric, human-centric view. Our framework defines complementarity and counterfactual harm through set-based outcomes. The AI's goal is to recover what the human misses without degrading what the human already knows. This formulation allows us to provide rigorous, finite simple guarantees on the reliability of the interaction. A more distantly related line of work focuses on incentivized exploration. Here, the AI acts as an information designer, strategically revealing or hiding data to steer humans toward better actions. This includes limiting the AI's exploration so users don't get frustrated and quit the platform 11, or providing incentives to convince short-sighted humans to make fairer, less biased decisions. 35. Other researchers explore how to selectively reveal information to encourage humans to try new options. 32-34. While these studies provide valuable insights into human AI dynamics, our approach is built on a different set of priorities. Instead of managing a population of users by strategically revealing information to new people at each step, we focus on an ongoing dialogue over multiple rounds. Our goal isn't to manipulate what a person sees or direct them toward a choice, but rather to construct a reliable, evolving interaction. Human reliance on algorithmic predictions. A substantial literature studies how humans actually use algorithmic predictions and understanding how the timing and presentation of AI outputs influence human judgment. 23 empirically show that human practitioners can often identify and override erroneous algorithmic scores in high-stakes settings, emphasizing the critical importance of maintaining human autonomy. In a similar vein, 12 examined how the presentation of confidence metrics impacts a user's inclination to depend on AI predictions, finding that the perceived alignment between the human and the machine influences the utility of the tool. 44 argue that algorithmic suggestions often function as behavioral defaults, where the perceived cost of deviating from a recommendation fundamentally shifts human preferences. This anchoring effect is further detailed by 25, who found that the specific sequence of interaction, whether AI results are displayed before or after a provisional human judgment, significantly alters diagnostic agreement and perceived utility in clinical radiology. To mitigate such over-reliance, study proposed a cost-benefit framework illustrating that explanations can curb anchoring if they sufficiently lower the cognitive effort required for a human to verify the AI's logic. 18 categorize how internal heuristics about task outputs and machine limitations determine whether a user successfully applies an explanation to override a fault prediction beyond the content. 25. For the AI's output, the structural protocol of the interaction itself plays a critical role, as evidenced by the study of double reading workflows by 15. In the domain of software engineering, 46 utilize a utility-guided approach to selectively withhold code suggestions that have a high likelihood of rejection, thereby reducing the verification burden on the programmer and improving overall efficiency. This empirical body of work is complementary to ours. While these studies investigate how humans actually behave when using AI, we focus on whether counterfactual harm and complementarity are the correct objectives to regulate in multi-round interactions. We design an algorithm to strictly enforce these objectives without making any assumptions about the human's internal logic, and show that by controlling these AI side metrics, we can indirectly guide the collaboration toward better outcomes, even though we treat the human as a black box and exert no direct control over their choices. See crowdsourcing study details and interface. This section provides additional details on the collaborative shape counting crowdsourcing experiment described in section 6.2, including the recruitment procedure, task interface, and image generation methodology. See Step 1 participant recruitment and study protocol. We conducted our crowdsourcing study through Prolific 4, an online platform for recruiting research participants. A total of 50 participants were recruited, with participants assigned to each of the 3 algorithm conditions A, B, and C randomly. Participants were required to be fluent in English and have a minimum approval rate of 95% on prior Prolific studies. Sequential participation protocol. A critical aspect of our experimental design is that participants were required to complete the study sequentially. We configured the Prolific study to allow only one active participant at any given time. This constraint is essential for maintaining the validity of our online threshold updates, because our algorithm adapts its confidence thresholds based on cumulative error rates across all prior interactions. Concurrent participation would introduce race conditions and potentially violate the sequential guarantees of our framework. Once a participant completed all assigned 20 trials, the next participant in the queue was permitted to begin. Algorithm assignment. Upon starting the study, each participant was randomly assigned to one of 3 algorithm configurations using a round-robin assignment scheme tracked by error-rates. Database top 5 has ensured balanced allocation across conditions while maintaining the sequential integrity of each algorithm's threshold state. The assignment was performed server-side, and participants were unaware of which algorithm variant they were interacting with. Each algorithm instance maintained its own global state, meaning that participants assigned to algorithm F attributed to a single continuous stream of interactions with shared adaptive thresholds. 4 https://www.prolific.com/5 https://eo26. Compensation. Participants were compensated at a rate of $12 USD per hour, with a median completion time of approximately 15 minutes for the full 20 trial session. Task description. Figure 6 shows the task instructions presented to participants at the beginning of the study. The instructions explain the collaborative nature of the task, the structure of each trial, 2 rounds of interaction with the AI assistant, and the mechanics of submitting guess ranges. C.2 Image generation and difficulty levels. We generated a dataset of synthetic images containing 3 types of shapes: triangles, squares, and stars. Each image was procedurally generated with varying numbers of shapes distributed across the canvas with randomized positions, sizes, and colors. The use of synthetic images allowed precise control over ground truth counts and enabled systematic manipulation of task difficulty. Images were organized along 2 dimensions: bucket based on the total number of shapes and difficulty based on visual complexity. Specifically, bucket images were divided into 3 buckets based on the number of distinct shape types present in the image. Bucket 1, images containing only 1 shape type, for example only triangles. Bucket 2, images containing 2 distinct shape types, for example triangles and squares. Bucket 3, images containing all 3 shape types, triangles, squares, and stars. Difficulty: within each bucket, images were further classified into 3 difficulty levels based on the total number of shapes present: easy, low total shape count, fewer objects to track; medium, moderate total shape count; hard, high total shape count, many objects competing for attention. Figure 7 presents representative examples from each bucket difficulty combination, illustrating the range of visual complexity in our dataset. To create information asymmetry between the human and AI participants, the AI assistant, powered by Gemini 2.0 Flashlight 28, received a degraded version of each image. Specifically, we applied a salt and pepper noise filter at an extreme intensity level, which randomly replaces a substantial fraction of pixels with either black or white values. This degradation ensures that the AI's probability estimates are imperfect, creating a realistic scenario where neither the human nor the AI has complete information. Figure 8 shows examples of the noisy images provided to the AI alongside their original counterparts. C.3 user interface. The study was conducted through a custom web application. Below we describe the key interface states encountered during each trial. After the initial image viewing period, 1 second in round 1, 27. 0.5 seconds in round 2, the image is hidden and participants are prompted to enter their guess. Figure 9 shows this intermediate state, where participants can see the AI's prediction set from a current round and must submit their own 3-integer range estimate. The interface displays the current round number, the target shape type, and the AI suggested range. Upon submitting their final guess, participants are shown a summary of the complete interaction. Figure 10 displays this completion state, which reveals 1. The original image for reference, 2. The full history of both rounds including the human's guesses and the AI's prediction sets, 3. The ground truth count, and 4. Whether the participant's final guess contained the correct answer. This feedback helps participants calibrate their performance across trials. To ensure data quality, we implemented several safeguards. Attention checks: participants who submitted identical guesses across more than 80% of trials were flagged for review. Roman 2 response: time filtering: trials with response times below 500 ms indicating random clicking were excluded from analysis. Lastly, Roman 3 completion requirement: only participants who completed all 20 trials were included in the final analysis. DLL and simulated experiment details. In this section, we report the exact prompt templates used to the DLL and simulated medical diagnosis. Test for reproducibility. Our setup instantiates 2 agents. A human agent GPT-4o mini. The human agent only observes patient demographics and chief complaints/initial symptoms. Roman 2 and AI agent deep sea chat. Importantly, the AI does not observe the patient demographic information. Both agents output JSON only. Prompt templates is for the notation clarity. We use the following placeholders inside templates. Label space. The full diagnosis label list size Y. Human info. Demographics plus chief complaints/initial symptoms what the human can't see. AI info. Full clinical picture what only the AI can see. Round. Current round number. History. Truncated competition history most recent turns. Human set. Humans current differential set for their top 2. AI set. AI's current prediction set 28. AI agent deep sea chat. System prompt: you are an AI clinical decision support system helping with differential diagnosis. Possible diagnosis: Y conditions. Label space. For information, you have access to some clinical evidences including symptoms, physical exam findings, and test results. The human physician can see the patient's age, sex, and chief complaint with initial symptoms. Return format JSON only. Reasoning: 1-2 sentences about your clinical reasoning. Probabilities. Diagnosis. Diagnosis prob. 0-1. Important. The diagnosis field must be one of the exact names from the list above. Include all diagnoses with meaningful probability 1%. The probability should sum to approximately 1.0. Use clinical evidence to narrow the differential. Human agent GPT-4o mini. System prompt round 1. Initial assessment: you are a physician seeing a patient for the first time. Possible diagnosis: Y conditions. Label space. For information, you can only see the patient's demographics and chief complaints/initial symptoms. You do not have access to detailed clinical findings, exam results, or tests. Your test round 1 initial assessment based only on the initial presentation. Provide your top 2 most likely diagnosis. Return JSON. Reasoning: your clinical reasoning based on demographics and chief complaint. Top 2 diagnosis. Most likely. Second likely. Rules: 1. Top 2 diagnosis must contain exactly 2 items. 2. Each item must be the diagnosis name copied exactly from the list above. 3. Use your clinical judgment based on the information available. 29. Human agent GPT-4o mini. System prompt rounds T greater or equal to 2. Collaborative updates: you are a physician collaborating with an AI clinical decision support system. Possible diagnosis: Y conditions. Label space. For information, you can see the patient's demographics and chief complaint. The AI has access to detailed clinical findings you cannot see. Collaboration rules: 1. Think about the AI's clinical evidence. The AI has physical exam findings, test results, and detailed symptoms. If the AI suggests a diagnosis you didn't consider, the AI likely has clinical evidence suggesting the diagnosis. The AI does not have access to the patient demographics. Its judgments are based on complementary evidence you cannot observe. 2. Update your assessment each round. If the AI suggests diagnosis you didn't consider, add them to your set if you believe the diagnosis is likely. Do not stubbornly repeat your previous answer. We evaluate each round based on whether the AI is disagreeing or agreeing with your proposal. 3. Sorting rules: only stop should continue equals false if your likely diagnosis appears in the AI set you agree with AI and the AI set is reasonably small given the inherent uncertainty in the case. 4. Must continue should continue equals true if here you do not believe the AI set contains the true diagnosis. The AI set is too large to be helpful for clinical assessment. Return JSON. Reasoning: how does the AI suggestion change your thinking? Top 2 diagnosis. Most likely. Second likely. Confidence. 0.0 1.0. AI set analysis: what clinical findings might the AI have seen? Should continue. True or false? Why stop or continue? Confident the AI set contains the true diagnosis. Stop. If not confident, continue and explain what is missing. Critical rules: top 2 diagnoses must contain exactly 2 diagnosis names from the list. You must reassess your top 2 diagnoses each round based on the conversation, available information, and your belief. 30. Use message context templates in addition to system prompts. Each agent receives a structure register message that provides the visible patient context, and Roman 2 carries forward the collaboration state sets and limited recent history. We include these templates for completeness. Human agent. User message round 1 context. Patient presentation. Human info. Round 1 initial assessment. Based only on the information above demographics and chief complaint, provide your top 2 most likely diagnoses. Note: you do not have access to detailed clinical findings, physical exam results, or additional symptoms. AI agent. User message round context. Patient information. The physician has access to demographics information you cannot see. Human info. Clinical evidence available only you can see this. AI info. Round. Physician's current differential. Human set. Use the clinical evidence available to provide an accurate differential diagnosis. The physician can only see demographics and the chief complaint you can see. Complementary clinical evidence. Conversation history most recent turns. History 31. Human agent. User message round context. Patient information what you can see. Human info. Round AI's differential AI SET diagnosis. The AI has access to the complementary clinical evidence, all symptoms, physical exam findings, etc. that you cannot see. Based on that clinical evidence, the AI suggests these diagnoses. AI set. Recent history most recent turns. History. Important. 1. The AI has clinical findings you don't have. Their suggestions are informed by complementary evidence. 2. If the AI suggests a diagnosis you didn't expect, they likely believe they have supporting symptoms/sense. Stopping check. Do you believe the AI set contains the true diagnosis? If yes and AI set size is reasonably small, you may stop should continue equals false. If no, you must continue should continue equals true. Medical test context. DDX plus case instruction and interaction protocol: we build each episode of interaction from a single DDX plus patient record, adding the case to a fixed diagnosis label space and enforcing the information asymmetry described above. Each episode proceeds according to the following multi-round protocol. 1. Round 1 human initial: the human agent receives demographics and initial symptoms and outputs an initial top 2 diagnosis set. 2. Round TAI response: the AI assisted outputs a full probability distribution overall diagnosis. To mitigate potential LLM hallucinations and ensure a valid distribution, we post-process and normalize these probabilities such that they sum to 1. The conformal algorithm then utilizes these normalized probabilities to construct a prediction set CT based on the current thresholds for counterfactual harm and complementarity. 3. Round T plus 1 human update: the human agent reviews the AI's prediction set, updates their top 2 differential, and decides whether to terminate the session based on the predefined stopping rules. 4. Termination and update: the interaction continues until the human agent decides to stop, where the interaction reaches a maximum of max rounds equals 6. Once the session concludes, the ground truth GT for the case is revealed. The online adaptive algorithm then observes whether a CH or comp error occurred during the session and updates the corresponding thresholds to maintain the target error rates for the next episode. 32. Extended experimental results. E.1 extended crowdsourcing convergence results. We present the empirical convergence of the adaptive thresholds for algorithms A and C in the collaborative shape counting test. As demonstrated in figure 11, the online algorithm successfully regulates the target error rates across different configurations. The stable convergence of the cumulative average running error to the pre-specified epsilon targets confirms the robustness of the adaptive mechanism in real-world human-AI interactions. E.2 extended LLM simulation convergence results. For further validate the finite temporal guarantees in the medical diagnosis test, we provide convergence results for additional configurations of the target error rates. 33. Figure 6 task instructions presented to participants at the start of the crowdsourcing study. The instructions describe the collaborative shape counting task, explain the two-round interaction structure, and clarify how to interpret and respond to the AI assistant's predictions. 34. Figure 7. Temple images from the shape counting dataset, organized by bucket rows and difficulty columns. Bucket 1 contains images with low shape counts 315, bucket 2 contains medium counts 1630, and bucket 3 contains high counts 3150. Difficulty increases from left to right, with hard images featuring greater shape density and visual overlap. 35. Figure 8. Sample visualization of most degraded images versions. Bottom row used as input for the AI assisted. The extreme salt and pepper noise obscures fine details, ensuring the AI's predictions are uncertain and creating a meaningful collaboration dynamic where both human and AI contributions are valuable. Figure 9. Intermediate interaction state of the user interface. The image is no longer visible, and the participant must submit it as a continuous range of free integers after observing the AI assistant's prediction set. The interface shows the target shape type, current round, and the AI's suggested range. 36. Figure 10. Trial completion state showing the full interaction history. The interface reveals the original image, displays both rounds of human-AI interaction including all guesses and AI prediction sets, and indicates whether the participant's final answer contained the ground truth. This feedback free interviews after each of the 20 trials. 37. Albe, CH epsilon CH equals 0.05. B albe, comp epsilon comp equals 0.5. C oxy, CH epsilon CH equals 0.05. D oxy, comp epsilon comp equals 0.7. Figure 11. Empirical convergence for algorithms and NCA in the crowdsourcing test. All plots track the cumulative average running error, AVD error equals 1. TPT, I equals 11 error I for counterfactual harm left, and complementarity right as they stabilize at their respective target values. 38. Config 1, CH epsilon CH equals 0.05. B config 1, comp epsilon comp equals 0.7. C config 2, CH epsilon CH equals 0.05. D config 2, comp epsilon comp equals 0.25. Figure 12, empirical convergence in the LLM simulated medical test across varying configurations. Plots demonstrate the algorithm's ability to track AVD error equals 1. TPT, I equals 11 error I for both CH and comp metrics under different target regimes. 39.